Thank you. Can you hear me? Okay. I'm a second year PhD student.
No, we can't hear you.
Yes, you can speak.
Okay, thank you.
Yeah.
Okay. Yes, I'm a second year PhD student at Graduate School of Mathematical Science, University of Tokyo. First,
Can you speak a bit loudly? All the volume is full.
yes, first, I'd like to express my gratitude to the organizers and everyone for giving me this opportunity.
Volume is full.
Okay.
Already volume is full, so yeah, speak a bit loudly. You have to speak a bit louder.
Because already his volume is full.
Yeah. Here also.
Okay. Okay. Yes. Yes. In this talk, I'd like to talk about compatibility of in the context of signed bijections. This concept allows us to measure naturalness of signed bijections. First, I present a combinatoric problem which serves as motivations of my research. That is ASM DPP bijection problem, which is also explained in Professor Di Francisco's talk the day before yesterday. ASM means alternating sign matrices and DPP means descending plane partitions. These objects both have a concept of rank, and it is known that there are the same number of each object for each rank. For example, there are 7 ASMs of rank 3, and there are also 7 DPPs of rank 3. These are the list of them. This equilibrium was conjectured in 1983 and probably in 1996, but there is no algorithm to construct a bijection between them. I briefly mentioned the connection between ASM and integrable systems. First, there is a bijection between ASMs and some configuration of the 6-vertex model with some boundary condition. Furthermore, ASMs appears in the expansion formula of the lambda determinant, which is related to the infinity T system. Return to the perspective of bijective combinatorics. Recently, partially bijective proof was given to the ASM DPP problem by Fisher and Konvalinka. They construct a bijection between this Cartesian product and this. We can complete the proof by induction. So I refer to this as partially bijective because their proof is entirely constructive, but they did not construct a bijection between ASM and DPP. And the construction used signed sets and signed bijection. So the construction is a bit complicated and the combinatorial interpretation is not clear. So my goal was to simplify their construction to make it more natural. However, which bijection is more natural is controversial. So to measure naturalness, we consider a compatibility of signed bijections. Before explaining the definition of compatibility, I explain some basic definitions. First, an alternating sign matrix of rank n is n times n matrix whose entries are 0 or plus minus 1, and non-zero entries appears alternately in each column and row, and such that their sum is 1. Namely, non-zero entries appears as a 1, minus 1, 1, minus 1, 1, and ending with 1 in each row and column. The number of ASM of rank n is given by this formula. And as I mentioned earlier, the number of DPPs of rank n is also given this formula. For DPP size, this is given in 1979. For ASM size, I explained it. Next, the definition of DPP is a bit complicated, so I omit it. But DPP is a semi-standard shifted Young tableau subject to some special condition. Namely, the shape of DPP is parameterized by a strictly partition. For example, 4 to 1, then the shape is as this. And entries decrease, weakly decrease along row, and strictly decrease along column. And a DPP satisfy some special condition stating here. And next, I define a sign set. A sign set is a pair of finite sets such that their intersection is empty. And the support of S is defined as this. And the size of a sign set is defined as this. And next, I define a signed bijection. In Fisher and Konvarika's paper, they refer to this as bijection. So I use the same term. A bijection phi from S to T is a bijection between this disjoint union and this disjoint union. A bijection can be recognized as a quadruplet of bijections. First one is a bijection between a subset of S plus and a subset of T plus. Second one is between a subset of S minus and a subset of T minus. And third one is the rest part of S plus and the rest part of S minus. And last one is the rest part of T plus and the rest part of T minus. By this definition and the definition of size, if there is a bijection from S to T, then the size of S and T coincides.
Sorry, why did you draw the arrows, the horizontal arrows and vertical arrows differently? Did you mean the horizontal arrows are involutions?
Yes, this is an involution.
It says, but these ones are not?
Yes, this is also an involution, but
sorry, but
bijection between this. This is a bijection between a subset of S and a subset of T. This is a bijection between a subset of S plus and a subset of S minus, and also this is an involution sign reverse involution on this set.
Okay, why didn't you draw that vertical arrow also like that? Is there a reason? I mean,
there is no reason.
Okay, thanks.
Because I want to this notation. This notation is derived from this figure because this cycle means this involution. So there is no mathematical reason. Thank you. We can define some operations on sign sets and bijections. Sign sets are for operations, these operations, and these definitions are intuitive and easy to understand. On the other hand, bijection allows for operations such as composition and Cartesian product and disjoint unions. We can define Cartesian product and disjoint union straightforward, but the definition of composition is a bit complicated, and this hinders on intuitive understandings of Fisher and Konvarika's construction. Let me explain the definition of composition in more detail. First, a citation phi from S to T can be represented by a graph as this. Here, each element S is related to phi S. Then a citation psi from T to U is also represented by a graph, and these two graphs can be overlaid. Here, the degree of each vertex in this graph is at most 2. So each connected component is line or cycle. By associating edges of each line graph, we can obtain a new graph. And indeed, this is a graph representation of citation from S to U. It is not so obvious, but we can prove this easily. So this is a definition of composition.
And what do you do with the closed loops? You ignore them?
We ignore this.
You ignore.
And now we define a compatibility. The motivation to define a compatibility is this. How can we measure naturalness of a suggestion? Let me begin with a formal definition. A statistic of a signed set is a function on at least its support. Let it be a statistic of S and T. Then a suggestion phi from S to T is compatible with eta if for all elements S of the support of this holds, namely eta phi S is equal to eta S. That means the value of eta is preserved under the action of phi. I explain how to use the compatibility to measure the naturalness. Basically, we consider suggestion more natural if it is compatible with finite statistics. But being merely fine is meaningless because, in fact, for any given suggestion, we can construct most finite statistics that is obviously compatible with it, because this can be constructed by each vertex, relate each vertex to the connected component it belongs to, and formally that can be defined by this. However, this statistic does not reflect any structure of S or T, so it is meaningless. So we can translate the naturalness of suggestion to the naturalness of statistics by using the compatibility. So it is important to have compatibility with meaningful statistic, but in general case, we don't know what meaningful statistic is. But if there is a result of refined enumeration, we can use them as hints. Returning to the ASM problem, there is a refined enumeration which is done by Bauland, DeFrancisco, and Ginjustan. There is a certain quadruplet of statistics on ASM and DBP. The statistics on ASM side is the curve number of the one in the first row, and the number of occurrence of -1, and the inversion number, which is defined as this for ASM, and the curve number of the one in the last row. I explain the outline of my research. Fish and Convericker's work is divided into two papers. In the first paper, they introduce specific Gelfand Zetrin patterns, and they construct a suggestion between ASM and SGT. In the second paper, they use this suggestion to construct a bijection between the Cartesian product of pertaining to ASM and DPP. This suggestion constructed in the first paper can be considered as a combinatorial realization of an operator formula, which is an important formula for enumerating ASM. So our goal is to simplify this suggestion and make it more natural. My research also be divided into two main parts. At the first step, we extend this definition of, we try to extend the definition of for statistics, but in practice, we succeeded in extending the two statistics considered in refined enumeration. One is the current number of the one in the first row, and second one is the inversion number. First one is relatively obvious, so we focus on the inversion number. We extend the definition of the inversion number to SGT and some intermediate combinatorial object, which appears in the construction of the suggestion. And in fact, the Fisher and convergence construction is not compatible with the inversion number, so we modify their construction to make it compatible with the inversion number at the second step. At the first step, we extend the inversion number to SGT. At first, originally, inversion number is defined on permutations, and we extended to the ASM by the refined enumeration, and there is a clear bijection or suggestion between ASM and monotone triangles and generalized monotone triangles, so we can extend the definition along the clear bijection or suggestion. So I omit the detailed definition of GMT and SGT, but their appearance is as this. They are defined as a pair of some triangular array and some triangular array of arrows. Then the definition, the inversion number of GMT is the number of uppermost right arrows. There is a suggestion between GMT and SGT, but it is complicated, so we cannot extend the definition along this suggestion. In practice, we find good definition for of the inversion number for SGT, which is the number of downward left arrows. So we adapt this as the definition of SGT. So yes, this is a construction of a Fisher and convergence suggestion. Main part is constructing a suggestion between GMT and SGT that demonstrates that SGT has same recursion system as GMT, and this is constructed by compositing four suggestions, and we can inspect which part is not compatible with the inversion number, by extending the definition to each intermediate combinatorial object. And 4 is not compatible with inversion numbers. So we modify this part, and some technical reason we omit phi 3 and modify phi 2 a bit. We can simplify the Fisher and convergence construction.
So there's no phi 2.
Sorry? So phi 2.
There's no phi 2 anymore?
Phi 2 is very easy suggestion. APN minus 1 is becomes APN. Just attach some arrows by this suggestion. So by simplifying phi 3, we cannot use phi 2.
Okay.
Yes. Yes. This is my main result. As a result, especially this is a bit important. We construct a suggestion between GMT and which is surjective to ASM, and some generalization of SGT are compatible with N+3 statistics. These N+3 statistics are given by a refined elimination, which is done recently. This is a good example of application of compatibility, I think. Okay, that's all. I think this framework can be used to many objects in integral combinatorics. That's all. Thank you.
Okay, thank you.